Okay, so welcome back. Now we're going to do the third corollary. The third corollary, or what I call Theorem 5, is for increasing and decreasing functions. So in this case it says, let f be continuous over the closed interval ab and differentiable over the open interval ab. So we've seen that set up before, right? Now, given that, then if f prime of x is positive or greater than 0 for all x in the open interval ab, then f is an increasing function over the closed interval ab. Likewise, similarly, if f prime of x is negative or less than 0 for all x in the open interval ab, then f is a decreasing function over the closed interval ab. Okay, so what this is saying is that basically if we have a continuous function over the closed interval and a differentiable function over the open interval, then if the derivative, or the slope, in other words, is positive over the interval, over the open interval, then we have an increasing function. If the slope, the derivative, i.e. the slope of the function is negative over the interval, the open interval ab, then the function is a decreasing function. Okay? So I'm going to go through the proof for part I, and part II is done similarly. Okay, so I'm going to again just follow along in your notes right underneath the proof, or right underneath the theorem, to start the proof. So the proof starts with an assumption. Okay, so we're going to suppose f is not an increasing function. Suppose f is not an increasing function. On I. So that would mean that there would exist an A and B on I. Then there exists A and B in I, such that A is less than B, but f of A f of A would be greater than or equal to f of B. Okay, now, so again, since we're supposing that f is not an increasing function on I, then we would say that, hey, there's got to be a couple of points where the function at the left, right, the function at A, is actually bigger than or equal to the function at B, right, if A is less than B. Okay, so what we're saying is that it's decreasing at some point, right? Okay. Now, since f is differentiable, on I, or I should say, since f is a differentiable function, over I, then we can use the mean value theorem for the interval from A to B. By the mean value theorem, there exists C in the open interval from A to B, right? So we're going to apply the mean value theorem to this open interval inside I, such that f prime of C is equal to f of B minus f of A over B minus A. Now, since f of B, how do I want to say this? Yeah, since f of A is greater than or equal to f of B, f of B minus f of A is going to be negative, greater or less than or equal to 0. Okay. Also, the fact that also A being less than B tells us that B minus A is greater than 0, right? Hence, f of B minus f of A divided by B minus A has to be what? Well, if the top is less than or equal to 0 and the bottom is greater than 0, so that means this quotient has to be less than or equal to 0. And so hence this is less than or, and of course f prime of C. Okay, which implies f prime of C is less than or equal to 0. Now, hold on a second, is that right? Hold on a second. Since f, A is less than B, f of A is greater than or equal to f of B, so okay, so now here's where we're at. See this? This is where it leads to a contradiction. However, what are we assuming in the theorem? We're assuming, says, let f be continuous over the closed interval ab and differentiable over the open interval ab. If f prime of x is greater than 0 for all x in the open interval ab. So that's one of the assumptions that we're making. The other assumption is we suppose that f is not increasing. But by supposing that f is not increasing, it leads to the conclusion that f prime of c is less than or equal to 0. However, what do we know? What are we assuming? We're assuming that f prime of x is greater than 0 for all, for all x in I. So there's where we end up with a contradiction. So that means our original assumption we started with is incorrect. So therefore, f is an increasing function. Over I. And we're done. Have a great day.